Okay, hello everyone. We are Tomasz Bartczak.
And Ireneusz Gawlik.
And we are working at Allegro. And we're going to talk about learning to rank. All right, so first, a few words about our company. So Allegro is the biggest e-commerce site in our region. And that's a go-to destination when it comes to online shopping in Poland. All right, and also a few words about ranking before we talk about learning to rank. So basically, ranking is a key part of any search engine, and that's definitely a key part of Allegro. And back in the days, ranking function used to be handcrafted. But now with the advent of machine learning, we want to have good algorithms that will provide personalized and more accurate search results. So all of those machine learning algorithms that work for ranking have a coin term, and that's learning to rank.
Yeah, so to summarize, learning to rank is a machine learning subfield in which we aim to train a model that will order documents for a query. And being a supervised learning approach, we need some grand true labels, and collecting them through some human judgment from human experts is quite expensive and time-consuming. So in practice, we usually rely on an implicit feedback. So feedback provided by users through their behavior, through what they do in the search engine. So this is how we formulate learning to rank in e-commerce setting. We treat offers as documents. We collect their vector representation. We convert user and query to a context and combine it with some true labels about whether a particular offer was interesting for a user. And before we dive deep into how to solve such a task, let's think about the metric that we are going to use to evaluate ourselves. And a typical one for ranking task is NDCG, which stands for Normalized Discounted Cumulative Gain. And so on the right, you see a curve for a single value of a discounted gain of an relevant document presented at a specific position. So we can see the curve is really steep, and it puts much emphasis on the top few positions in the list. And we'll talk about it maybe a moment later. Why is that? And you sum over all the relevant documents in the list and normalize it by dividing it through an ideal DCG, so the one that would be perfect for a given search result list. So the range of the metric is between 0 and 1.
All right, now we're going to talk about different learning to rank methods. We divide them in a few groups, and those groups are point-wise, pairwise, and list-wise approaches. So first, we're going to talk about the point-wise approach. Here, basically, we have some features that describe a given document, maybe some additional context. And what we do is we basically train a classifier to classify for clicks or for some other actions that are of our interest. And that classifier might be, as simple as logistic regression trained with cross entropy. So that approach obviously works. But it doesn't take into account the context that the document is within. So basically, it's just a document in isolation. It doesn't look at other documents that co-occur at the same listing, and that might be actually a valuable information. The other thing is that we are not optimizing for NDCG, which is like our metric of interest. We are just optimizing our classifier, but it has been shown that perfect classification leads to perfect ranking. Other approach, that's a pairwise one. We are going to talk about that by example of RankNet. In this model, we train a neural network to express the scoring function, but that's not the most important part. We can use any function. The most important part is how we optimize, is how we define our optimization procedure. So in this case, we have some documents, let's call them UI and UJ. And what we are interested in is the probability that the user would prefer one document over the other. And that's what we try to optimize. And we do that, as usual, with cross-entropy. In the end, we can take advantage of the fact that we are comparing documents in pairs and not in isolation, and that provides better results.
Okay, so the last approach would be a listwise one, and here we want to build some kind of intuition about what's really the key point in a listwise approach, not going into the details of specific implementations. So we can see two search result lists with two relevant documents on each, marked with those blue lines. And you can see that the left one has more pairwise errors than the right one, although it has much better NDCG value. So you can see that this is a kind of a good example of where those approaches would differ in terms of what should be optimized and for a given situation. So with those arrows on the right, we show the gradients that would be formed by pairwise. Those would be those black ones algorithm, and the listwise one that would try to optimize NDCG. Those would be these red arrows. So you can see that they try to move not the same documents at first. So the stronger the strength of the gradient is different here. So we try to optimize the whole result list at once, and we would like to optimize our final metric, of course. This would be the best. However, it's hard to optimize NDCG directly using gradient-based method because its derivative is not defined everywhere or is zero. So those approaches try to avoid this issue in some ways. For example, lambda rank is assigning a weight to a pairwise cost for every pair that is weighted by difference by change of NDCG given those pair of documents would be swapped. So this kind of brings the optimization of NDCG with pairs, so to say.
All right. Now having some knowledge about those different approaches, we're going to talk about how we actually implemented our production system, how we implemented learning to rank at our company. So before we could train any model, we needed to collect our data set, obviously. And what was of our interest was the context in which someone was looking for something, obviously offer features, and the list of actions. So when we wanted to optimize for click, that would be click. For transaction, that would be transaction. And well, it was not a trivial task having our very huge platform and diverse data sources. But then we managed to create such a data set, and that included offer features, that included some custom offer aggregates that we have, obviously some user features, search events, lots of front-end events. And whenever it was possible, we wanted to use aggregated data sources. And that's for a reason that it basically sped up our experimentation. It made it possible to be more agile with checking different approaches. And currently, we gather approximately 200 million observations daily.
Okay, we train our model, which is an XGBoost model that is trained with a pairwise laws. XGBoost has some ranking scenarios implemented. And although we started with training with some pure Jupyter notebooks, we quickly moved to a suite of Python packages for dataset sampling, for training, for evaluation. That gave us like better control in the team over what's going on. And it allowed us as well to go for better experimentation, right? Running multiple jobs in parallel, configuring them, keeping the results. And it as well allowed us to tune hyperparameters with ease, which we'll see in a second. We keep our results in the TensorBoard, as you can see on the right. And let's dive into the hyperparameters a bit. So this kind of model, an XGBoost, a gradient boosting tree model, has several important parameters that will influence the final model score. So it's an important step to do it before going live. We used a hosted service in Google Cloud Platform that is implementing the Google Visio approach, and what we found out is that the obvious one, that early stopping for sure is a thing that will speed it up, especially if you run that many jobs. And that actually with those gradient boosted models, a small model, I mean not that many trees as we've expected initially, can perform almost as good as a large one, given you tune the hyperparameters even there. And we have found a few moments that we got like bad or unexpected results, and it came out that the reason was some of XGBoost quirk. So if you work with it, you should be aware that they exist.
Okay, now let's talk about feature importance. Once you have your model, it's good to know which features were actually important, which features brought some information into the model. And we've graded boosted trees. As with any complex model, it's not too easy to actually interpret your results. And with tree-based models, we usually go with metrics like cover, gain, weight. That's what's implemented in XGBoost. The only problem is that it didn't really correlate well with our NDCG improvements that we got when we included some new features into our data sets. So we went with some other methods. We investigated Lime and SHAP. Right now we are using SHAP, and you might have heard of it yesterday. Probably someone is going to speak about it today as well. Yeah, the next slide. Some issue.
Docker update, great.
Docker update.
Yeah, so maybe skip that. Okay, when working with this experiment, we were aware of a few things that existed in our data, and one of those was a few biases. And what I mean by that is, first of all, position bias, which is a natural tendency for people to look more at the top items. And there are other presentation biases for sure in our platform, for example, that are related to like visual markers, that some offers are highlighted, promoted, that affects like user behavior as well. And the idea in handling bias is to understand its influence on the data and use this knowledge to kind of debias the data for training. And one of the approaches, basic approach presented in one of works in the area, is to calculate a position-based propensity model, which will reflect how likely are people to investigate a document at given position. And because it assumes that before one could actually click a document, it must first examine it and then find it relevant. And we know that it both happened. But if we don't have one label for any offer, we don't know whether this offer was not relevant for a user, or maybe it was just not examined at all. So we can calculate that kind of model with a randomization or swapping experiment, and actually use an inverse of this propensity score to weight your training example, so that you give more weight to the more important observations. And maybe it will be more clear with this chart. So if this looks similar to the NDCG curve we showed at the beginning, you're right, because actually this red dashed line is an NDCG, and the blue line is a scaled propensity that we calculated in our experiment. So we can see they are really similar because they capture actually, it confirmed the same thing, that people tend to investigate more the offers on the top, and that's why this is the kind of the weights for the metric, and it can be used as weights for the training, but in an inversed way.
Okay. Now we would like to talk about how we incorporated some high-dimensional, some rich data into our graded boosted trees models. And the problem with graded boosted trees is that they don't really work well with rich data like images, obviously. And that's the reason why we resort to deep learning in those cases. And even though we would love to have end-to-end model trained fully with SGD, and that would probably solve that issue, that's just one of our future experiments that we want to do. For now, we have graded boosted trees models deployed to production that are actually running, and we would like to like make some use of some data, like textual data or images, into our ranking models as well. So what we decided to do is to create some additional features based on similarity metrics, like basically something that was covered in the previous talk in this hall. So we basically match search phrases with images or search phrases with titles in documents, and then calculate some similarity metrics, like cosine or Euclidean one. And basically, our objective while we train models that calculate those similarities is to maximize similarity of matching entities. When it comes to textual data, the obvious choice at the beginning was to go with word embeddings, and we tried word2vec, we tried Glove. It didn't provide us with any substantial gains. So we tried to look for something else. Now we are using StarSpace, that's library which was developed by Facebook AI Research. And with this library, we can actually provide some supervision into training. That's not purely unsupervised approach. We can provide some supervision, and that's, in our case, implicit feedback that we are using, like the same implicit feedback that we are using to train our learning to rank models. So we basically take some pairs like phrase and a title, and then try to minimize cosine distance between positive pairs, and then maximize the negative ones. So you can see that on an image, let's say that we have a phrase like latest iPhone, and we have iPhone XS and we have iPhone 6. During training, having that for that phrase, someone clicked on the latest iPhone, actually. We want to have an embedding for the phrase latest iPhone as close to embedding for iPhone XS, something blah, 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 like as close as possible and further away than iPhone 6.
Okay, how about images? So, of course, the baseline would be to take, as a representation of an image, take a high-level activation from some well-known ImageNet, network trained on ImageNet, and it was a baseline for us. But since having a general image representation would be valuable in multiple actually domains and products in our company, like it could be visual recommendation or visual search, then we decided to try to come up with a better way to get those representations. And first of all, we are assigning our own contextual data for the images. For example, train the network to predict some offer attributes or of a category, which should help it move it to our domain. And we are as well training an unsupervised models, both from the family of an adversarial network, namely GANs, and from the family of variational autoencoders that you might have seen on the second keynote covered. And what we do with this representation, if it's not clear, is that we have a representation of an image, but we don't have a representation for a phrase or for a query in the same space. So we follow a centroid-based approach. So for any query, we calculate a centroid of all the representations of clicked offers for this query, and then calculate the distance between those points for as a ranking feature.
Okay, now a few words on deployment. So first of all, one explanation. In sites like Allegro, we actually have lots of traffic. So we have thousands of queries per second, and we have almost 100 million offers. So that's a large space to search from. And that obviously provides some challenges. And what we needed to apply is a thing that is called multi-stage ranking. So first, if we have some query, let's make it red sum address. It lands into our search engine, but in our case, that's Solr. And in there, we have some static scores. For each offer, we have some static score, which is computed by some ranking model. And based on that, we have some ranked documents which are not really ranked in a contextual way. But then we can just take top N of those documents and take all the contextual information that we might have, let's say the phrase, some user features, maybe some other context which is totally independent from that, and apply our re-ranking model in our re-ranking engine, and then we get a list of re-ranked documents. What's really important is that both the ranking model and the re-ranking model is trained using learning to rank algorithms, and that's all based on our historical data.
Yeah, so one a thing that we've learned the hard way was verification of our deployment. So our data pipelines for the online and offline have much in common, but they differ a bit. For example, you've learned that we use aggregated data as much as possible for the training, but we need to rely on events and streaming data as much as possible for the production phase. So there is a bit of difference in what data comes to the model, and we need to convert both representations to the same feature vector, both when training and when deploying. And while we are working on a good solution for that, that will solve this problem, we employed a verification procedure that we run on our model candidate, and we compare feature distributions between what we had in training and what we have in our online data store, and we compare model scores distributions. And this we run it whenever we add a feature or a feature change, and it happened quite often in a dynamic environment. And it kind of protects us from covariate shift that could happen with our data sets. Okay, so we are slowly coming to the end of our slides, so we would like to share some results. So we trained our models. We found a nice improvement in the offline data set. And we deployed a few models as an A/B test to the production, and we got even better improvement. So we find that it correlates with each other, so it means good that we use a metric in a way that correlates with our final production metric. And this fact that the improvement in the production is better than what we had in training data can be justified by, the position bias that we talked about, and as well that we were using not a random sample for our training, but we've used data that was ranked by some previous version of search engine ranking that was there before. So that would be it. We have time for questions. Thank you very much for your attention.
Thank you guys for your talk. It was brilliant. I have a small question about you definitely have something like recommender system on the site, right? Did you try to apply or use the vectors or some data from recommendation system in your search algorithm for ranking or something?
Source of feedback, that's what you mean?
Yeah.
Not really. We have plenty of implicit feedback based on what users do.
Yeah, but I mean, you can learn your items representation in the recommender system as well, and you can try to use this one in the search as well. So I'm just wondering if you really thought about this approach, or maybe you try to use it or something.
Well, the kind of the recommenders that would work this way are currently being developed. They are not everywhere on the platform. So, and I think we have tried some time ago, but this idea is surely somewhere in our minds, but not yet baked very much. But yeah.
Yeah. Thank you.
Could be good.
Thank you.
Any question? Thanks for the talk. You talked about propensity, about removing the bias. And you said that you did some experiments. So there were experiments where you swapped randomly things on the website, right? You talked about unbiasing the searches. So I'm curious about this step. How did you do this?
Yeah, well, actually, it was a short experiment where we like the first page of the results was not the whole results was random, but the order of a top n documents was random there, and we could calculate this propensity there. So it happened once at some point of the time, there are methods that do not require actually randomization experiments, and they even try to jointly learn the bias model with the ranking model, but they are like on our experiment list because we didn't yet manage to find time for them.
Okay, thanks.
Questions? Okay. Thanks.
Thanks.